Hello, everyone. This short video is about a geometric interpretation of the meaning of the determinant. We'll see an interpretation in 2 dimensions and in 3 dimensions. For the 2 dimensions, look at this setup. Suppose you have 2 vectors in the plane, u and v. These 2 vectors, when you add them together, define a parallelogram of which they are 2 of the edges. The meaning of the determinant in this case is that if we take a matrix A whose columns are exactly the 2 vectors A and V, then the determinant of the matrix A will coincide with the area of P. And of course, you have to take an absolute value in case the determinant is negative. So the absolute value of the determinant is the area of the parallelogram. I will give you a sketch of why this actually is true, and hopefully it will be convincing. The reason why this is true goes through the rotation matrices that we worked with before. Consider these 2 pictures, our starting parallelogram P and a parallelogram P prime, which is what I get by rotating P back by an angle theta. Except the way I present it here, I want to think of it as starting from P prime and then rotating by an angle theta to get our original parallelogram P. The edges of P prime will be 2 vectors, v theta and u theta. And the only thing that I want to point your attention to here is that by our construction, v theta lies on the x-axis, so it has no y coordinate. Now we're going to do 2 steps here. First, I want to observe that rotating doesn't change determinants, and of course it doesn't change areas. Let's check about the determinants. So the determinant of the matrix whose columns are u and v, which are the rotated vectors, the original one that we started from, is the same as the determinant of r theta u theta and r theta v theta, because u is obtained by u theta from u theta by rotating by an angle, and v is obtained from v theta by rotating. So I just substituted these equalities in here. Now, if we look at this matrix, that is what we get by multiplying the matrix r theta with the matrix containing vectors u theta and v theta as its columns. And let's keep computing. Here's a fact which we haven't discussed just yet, but it's something that we'll see very soon, and it will become second nature. The determinant of a product of matrices is the product of the determinants. In other words, we can break this up as the determinant of the rotation matrix times the determinant of u theta v theta. Now, by the example in the previous video, the determinant of a rotation matrix is equal to 1. So this is just the determinant of u theta v theta, the matrix whose columns are vectors u theta and v theta. Okay, this is step 1. Applying a rotation matrix does not change determinants, and of course, it does not change areas. Now, step 2 is computing the area of our parallelogram P prime. The area of P prime, you can see it from this picture, is exactly computed by its base, which is v1, times its height, which is u2. It's the y coordinate of the vector u theta. That's what I wrote here. The area of the parallelogram P prime is v1 times u2. However, if you stare at this long enough, you'll realize that v1 times u2 is exactly the determinant of the matrix u1, v1, u2, 0, which is the matrix u theta, v theta. It is that determinant because we get 0 times u1 minus v1 u2, but I put an absolute value. So v1 u2 is the absolute value of this determinant. which is the absolute value of the determinant of u theta v theta. Now, piecing 1 and 2 together, we get our conclusion, which is that the area of the parallelogram P that we started from is the same as the area of the parallelogram P prime, which is the same as the determinant of the matrix u theta v theta. This is step 2. And by step 1, that's the same as the determinant of our matrix u v. And of course, I should put absolute values here. It's important not to forget them because determinants may be negative. So we want to make sure that we look at positive quantities. Something similar happens in 3 dimensions. In 3 dimensions, imagine you have a solid region like this parallelepiped. The volume of the parallelepiped is computed by the absolute value of the determinant of the matrix whose columns are the 3 vectors that are depicted here. Let's just have an example about that. If you were to have 3 vectors given like this, they would span a solid 3-dimensional region. And the volume of such region would be the determinant of the matrix whose columns are exactly the 3 given vectors. To compute this determinant, we can use a cofactor expansion, and I want to take advantage of the fact that there's a 0. So I'll do a cofactor expansion along the 2nd row, which means that I will have 1 times the determinant of A2, 1. I erase the 2nd row and the 1st column because that's where my 1 lies. I'm taking this guy, which is 1, 2, 1, 1. Except if I use cofactors, this 1 is in position 2, 1, which means that it has a negative sign in front because it's a -1 to the 3. The next entry is a -2, which has a negative sign, which is a positive sign in front by the cofactor expansion, and the corresponding matrix will be the one that I get by erasing the central rows and columns. So this will be the determinant of 1, 2, 1, 1. Let's wrap this up. We get -1 times, that determinant is 1 times -2. Plus -2 times, it's the same matrix, -2, which becomes what? 2 plus 4 is equal to 6. That is the volume of my parallelepiped. I should have put absolute values everywhere. Here they come. Of course, in this case, it doesn't matter because I got a positive answer at the end. I'll see you in the next video.